Okay, so on our last lecture, we introduced, we finished the part about solubility rules, and we discussed all different types of double displacement reaction. Okay, and one conclusion we reached is that in the end, that for a double displacement reaction to happen, you have to, okay, produce things like a precipitate or a molecular compound like water molecule or a weak electrolyte, a weak acid or weak base. Okay, the idea is for your double displacement reaction, now for it to happen, now any two ionic compounds, as long as they don't have common ions, you can always predict two possible products. All you need to do is exchange the partners for your positive ions and negative ions. So mix and match them. Okay? But whether the actual reaction happens or not, okay, is not just that you can make a new chemical formula. Okay? The real chemistry happens when you have something that you cannot completely break down. Okay? Because if all you have in your reactants and products are just strong electrolytes, soluble salts, strong acids, strong bases, well, your reaction is not going to happen. So, for example, if you have, let's say, NaCl reacting with CaNO3, okay? Now, you can exchange partner all you want, okay? Label the charge, and you find, okay, I'm going to make CaCl2 and NaNO3, okay, to match the charge. And then, of course, you're going to need 2 sodium, and you're going to end up getting 2 sodium nitrate as well. Okay, they don't share a common ion. You can always predict product. But does this reaction happen or not? If you look at everything here, things contain sodium soluble, so Na plus Cl negative, 2 of each. Containing nitrate, so soluble, calcium ion, 2 nitrate ion. Calcium chloride. Chlorides are only insoluble when you have silver, lead, and mercury 1. You only have calcium, so this is soluble. Break it down. And sodium nitrate is obviously soluble, about as soluble as it gets. Both ions are soluble ions. And then you realize, okay, I got 4 strong electrolytes, 4 soluble salts. Everything is a spectator ion. All 4 ions are spectator ion. And no net ionic equation. And what does that mean? There's no chemistry between these guys. Okay, you started with 4 free ions, you ended up with the exact same 4 free ions. No reaction. Okay, so this is why to make a chemical reaction happen, you gotta be having things in your equation like a precipitate, an insoluble ionic compound, a molecular compound, something that you cannot non-electrolyte, something you cannot dissociate, okay, or weak electrolyte or weak acid or weak base, which we talked about that you also can't dissociate, at least into ions completely in a full ionic equation situation. So that's why. Now, and in the end, okay, I do want to talk about a few special weak electrolytes. Okay, let's use this example. You have potassium sulfate reacting with hydrochloric acid. Okay, you should all be able to exchange partner and figure out predicting the product now. It's easy. Okay, +1, -2, +1, -1. So potassium is going to go with chloride, and you're going to have 2 of those, and then you're going to have H2SO3. Okay, and we know this reaction is going to happen because this is a weak acid. Okay, but when we're breaking this down into full ionic equation and net ionic equation, okay, anything containing potassium is completely soluble, so strong acid completely soluble, soluble salt completely soluble, and then now normally we said that okay, weak acid should stay in the molecular form, okay, and we could have wrote H2SO3, okay, and then this would be your spectator ion, and everything else is what it is. Chloride ion is the spectator, and then everything else gave you the net ionic equation. Now, but for this particular situation, when you're making H2SO3, okay, know that this is a kind of unstable weak acid. Okay, now what's going to happen is a molecule like H2SO3, okay, it won't fully dissociate. It's going to dissociate a little bit and give you some, H plus ions and sulfate ion. But majority of the compound, though, okay, instead of staying in this original molecular form, it actually break down, not dissociation into ion, but break down into 2 neutral molecules, okay, H2O and SO2. So the net ionic equation for this should be SO3 2 negative plus 2H, producing water and sulfur dioxide. So this is something that this particular weak electrolyte do. Okay, and this is why a sulfurous acid, H2SO3 is sulfurous acid, a sulfuric acid solution, okay, would always have this bad smell. Okay, why? Because you're not smelling the acid molecule in that case. You're actually smelling molecular sulfur dioxide. Okay, it stinks. Now, and there are 2 other weak electrolyte does the same thing. They're unstable as a big molecule, and it actually break down into 2 smaller molecules. Now, those are H2CO3, the carbonic acid. Okay, now it breaks down into water and carbon dioxide. And actually, now, this is the acid in soda. Okay, now every time you drink soda, you have that tingly feeling on your tongue, right? Now, why? Because what you have in soda is carbonic acid, and it dissociated a tiny little bit and gave you some very, very little amount of H plus ion, and the tingly feeling you have on your tongue whenever you drink soda is the H plus ion attacking your tongue. Okay, now, But H2CO3 molecule is also very unstable. Okay, under normal pressure and temperature, it would very easily break down into water and carbon dioxide. And this is why, okay, you have a soda bottle, okay, a new one is always sealed. Okay, why? To keep the pressure inside. Okay, keep the pressure on and stop your molecule from massively breaking down into carbon dioxide. And if you lose that pressure, okay, you could even hear the sound psst whenever you open a soda. And what's happening? Okay, carbonic acid breaking down, carbon dioxide molecule getting away. And also, an increase in temperature would also help your carbon dioxide in escape. And this is why your soda has to be stored, okay, in a sealed bottle. You want to recap it every time you didn't finish one, and you want to store it in the fridge, okay, because otherwise it's going to go flat. Flat means what? Carbonic acid breaking down into water and carbon dioxide. Carbon dioxide as a gas is going to escape. Okay, and the third type is ammonium hydroxide. We mentioned this back in the part when we talk about solubility rules. Okay, this is a very unstable molecule. It's going to break down into ammonia and water. Okay, this is why ammonia solution, okay, or you can really call it the ammonia solution as ammonium hydroxide solution, okay, always have a very stinky smell of ammonia. So if you see these three compounds, H2SO3, H2CO3, or NH4OH being made in your reaction as a product, break down into molecules. What molecules? This, and this. All right, so last little piece of conceptual nuggets. Okay. Mixture of three solutions. And now we're not going to talk about mixing, salts and acid and base. It's gonna make the situation very complicated. In here, we're only going to talk about three soluble salts. Okay. Now, when you're mixing two ionic compounds or salts, they're only going to exchange partner. The possibility of the product is only two. Okay. But when you mix more than two solutions or electrolytes, that always makes your product, okay, way more complicated. Why? Well, let me see this last example here. Three soluble salt solutions are mixed. Predict precipitate of the mixture. So there's supernitrate, barium chloride, and potassium sulfate. Now, if it's any of the if it's only two out of these three guys, okay, whether it's silver nitrate and barium chloride, or barium chloride and potassium sulfate, or silver nitrate and potassium sulfate, okay, it should be very easy for you to predict products or predict precipitates as long as you know your solubility rule. It's very straightforward. But when you have more, and when the situation gets more complicated, because now each of your positive ion have two more negative ions to try instead of just one more negative ion. It doesn't have a choice. Okay, now it does have a choice. Okay, it could run into any of the other two negative ions and possibly form a precipitate. So the important thing here is not, okay, just looking at the formula, know what's going to precipitate. It's more about, okay, let me make sure I take care of all the possibilities. I don't forget any of them. So the way that we handle this type of mixture of three solutions or more, okay, is always, well, let's take a list of our positive ions and negative ions. Okay, what are the positive ions in these three solutions? There's the silver ion, there's the barium ion, and there's the potassium ion. Okay, and then the anions, we have the nitrate ion, -1, chloride ion, -1, and sulfate ion, -2. Okay, so now, how do we make sure we don't miss anything? Well, silver was originally with nitrate. Now, it can try it out with chloride and sulfate. Barium is originally with chloride. Now it can try with nitrate and sulfate. Potassium is originally was with sulfate, but now it can try chloride and it can try nitrate. Okay, so total of 6 different possible products. Okay, so you could have AgCl, 1 and 1. Okay, you could have AgSO4, 1 versus 2, because the charge is +1 and -2, you're going to need 2 silver to bounce off the 2 negative charge on sulfate. Alright, so then barium could go with nitrate, barium could also go with sulfate. So therefore, barium nitrate plus 2 -1, so parentheses 2, and barium sulfate. Okay, now, and then eventually potassium can go with now nitrates or chloride. And then you have potassium nitrate and potassium chloride. Now, doing it this way, you can make sure you don't miss any possible combinations of products. Okay, but now it's asking you, okay, predicting precipitate. So these 6 possible products, which ones are insoluble? Which ones are insoluble? Well, let's see. Chloride. 3 ions make chloride soluble: silver, lead, mercury 1. So that is a precipitate. Okay. Number 2, sulfate. Rule number 4 of the solubility rules: sulfates are generally soluble except when combined with 6 positive ions, right? Silver, lead, mercury 1, calcium, strontium, barium. And silver obviously is top on the list, so this would be a precipitate as well. Barium nitrate. Anything with nitrate is going to be soluble, so this is not a precipitate. Barium sulfate. Okay, sulfate has barium as one of the 6 positive ions that precipitates it, so that one works. And then potassium nitrate, potassium chloride. Anything containing potassium would be soluble, and you don't have to worry about them. So 3 possible precipitates: superchloride, super sulfate, and barium sulfate. Okay, so if the amount of mixed electrolytes increase, the possible products is going to increase dramatically with more and more electrolytes mixed with each other. All right, so all of that so far are the conceptual things about solution chemistry. We spend quite a bit of time on it, okay, talking about all the possibilities of different type of double displacement reactions. And now, okay, so the next thing that we're going to be talking about in solution chemistry is not conceptual anymore. This is more numerical, okay? And here comes the calculation type and the number type of stuff for solution chemistry, okay? And that starts from the concentration of solution, okay? Now, what's concentration of solution? Essentially, it's the amount of dissolved solute in a given amount of solution, okay? Now, and what are the units of concentration of solution? There can be all kinds of units, and pretty sure that whenever you read the label of, let's say, a beer bottle, okay, you read the label, sometimes you find, okay, the solution is 5% alcohol, okay, C2H5OH, okay. That is a representation of concentration. What does 5% means? Every 100 grams of this beer would contain 5 grams of pure alcohol. Okay, so that's a way of representing concentration. You could also go, well, okay, grams per milliliter or per liter. Okay, for example, now a given soda, okay, a certain soda, okay, let's find that each 1 liter of this soda, it contains about 1.9 grams of carbon dioxide dissolved in it. Okay, as long as you show the amount, whether it's grams or moles, okay, of a given solute, now within a certain amount, in this case 1 liter of the alcohol, 1 liter of the soda, and in this case 100 grams of this beer you were dealing with. So concentration can have many different type of unit, okay, but the units we are going to be using here today, okay, focus on something that we learned before, okay, we're talking about molar concentration of solutions, okay, or you can call this molarity. Okay, we use capital letter M to represent it, okay? Make sure if you want to represent molarity, okay, you don't use the lowercase m, okay? Lowercase m in chemistry, in concentration, actually represents a completely different unit. And those of you who's going to move on to Chem 116, you're going to see this unit, the lowercase m concentration unit, a bunch over in that class. No. But in Chem 115, this is the one and only concentration that we focus on, okay? And the molarity or the molar concentration of a given solution is defined as the moles of solute dissolved in liters of solution. Okay, this is a very common unit in all kinds of chemistry labs, okay, and even in some other labs. Now, it's very easy for you to find a solution bottle labeled as something like, okay, this is a 6 molar HCl. What does that mean? That means if you take 1 liter of this solution, it's going to contain, okay, 6 moles of hydrochloric acid. And also, now, whenever we do the calculations, okay, there's an easy way to write the molar concentration of a given chemical. Let's say if we're talking about HCl here, you can simply write this as the concentration, the brackets here means the molar concentration of HCl is the solute of HCl in this solution is 6 molar. Okay, so don't be surprised on their on your future notes and on your future exams. You know, instead of writing the concentration equal to, I'm just simply giving you a chemical and a set of bracket to tell you, okay, here is we're talking about the concentration of this given chemical compound. All right, so how do we get the concentration? Well, you have 2 things. If you have those 2 things, the moles of solute and the liter of solution, you can always calculate the molar concentration or molarity. So here's an easy example. 0.25 mole of NaCl dissolved in 500 milliliter of solution. Okay, calculate molarity. Okay, now the concentration of sodium chloride, using bracket, should equal to mole of the sodium chloride divided by liter of solution. So 0.25 mole of sodium chloride over 500 milliliter times each 1 liter is 1,000 milliliters. So milliliter cancel, you now have liter on the bottom, you have mole on top. That's exactly what molarity constant unit is. Okay, so 0.25 divided by 500 divided by 1,000 to 0.5. So 0.25 divided by 0.5, 0.50 molar. And now, of course, for something like sodium chloride, this should be pretty easy and straightforward. But if you have take a sip of water. Now, if you have other ionic compound, especially the ones that contains multiple ions in their chemical formula, multiple positive ion, multiple negative ion in their chemical formula, okay, then you gotta be very clear about something. For electrolytes, okay, concentration of the compound and concentration of the ions, okay, vast majority of the time are not the same. Okay, what do you mean by that? Well, let's see a simple example. Again, what is each ion's concentration in a 0.60 molar aluminum sulfate solution? And so essentially we're asking you, what is the concentration of aluminum ion and what is the concentration of sulfate ion? Okay, how should I deal with that? Well, we have that number for the compound. Let's try to figure it out. Okay, so aluminum concentration should equal to, okay, you have that concentration in 0.60 mole of aluminum sulfate per 1 liter of solution. And I don't care about mole of aluminum sulfate. Each 1 mole of aluminum sulfate should contain 2 moles of aluminum ion. So moles cancel, you get 1.2 moles per liter. Use molar to represent it. Chloride ion. Okay, very easily, if you understand what we're doing here, then the concentration of the sulfate ion should be done the same way. 0.60 mole of aluminum sulfate times each 1 mole of aluminum sulfate could contain 3 moles of sulfate ion. And of course the result is 1.8 molar of sulfate ion. Yeah. And now, using the definition of molarity, okay, you can always go back and forth between the moles of compound and the volume of the solution, okay? Now, and also, we already know for a long time now, moles can be calculated into grams pretty easily with the help of molar mass. So let's take a look at the next example here. How many grams of H2SO4 is needed to make 400 milliliter of 0.60 molar H2SO4 solution. Okay, so we want the mass of H2SO4. Okay. How do we get mass of a compound? Okay, you can do stoichiometry if it's involved in a chemical reaction. This certainly is not needed. Now, so how do we get mass of sulfuric acid without a chemical reaction in stoichiometry? Well, if I can figure out a mole of H2SO4, I can always do that. All I need then is the molar mass. Well, how do we get moles of H2SO4? Well, you have something that already have mole in it, right? This is 0.60 mole of H2SO4 per 1 liter of solution. Okay, that's definition. Well, you look at this, you go, I want moles of H2SO4. I need to get rid of the liter. How do you get rid of the liter? You don't have liter, but you do have a milliliter. Okay, 400 milliliter is 0.400 liter. How do you get rid of liter? Multiply by 0.400 liter. And now you got moles of H2SO4. And each 1 mole of H2SO4 is 98.1 grams. All right, so mole of H2SO4 cancel as well, and keep my two sig figs. So 6 times 4. 98.1. So 23.544 grams. But since you only have two sig figs, so 24 grams of H2SO4 is needed. So that means if you put enough of water into 24 grams of H2SO4, okay, and get 400 milliliter of solution, that solution's concentration of H2SO4 is going to be 0.60 molar. Okay, and this, I got a lot of questions from people asking me, well, where do I get more questions to practice? And well, this can be made into a different concentration practice problem pretty easily. Okay, you can go, well, 23.5 grams of H2SO4 is made into 400 milliliter of solution. What is the concentration of H2SO4 in the solution? And actually, you can go say, what is the concentration of H plus ion in the solution? You can do all that, okay? And the way we're going to calculate it, we're going to turn this grams using the molar mass into number of moles, and number of moles divided by volume give you concentration, okay? And that will be the concentration of H2SO4. Okay, now, what is the concentration of H plus ion? And for that concentration of H2SO4, given all the values that you know from the previous example problem, you know this is going to be 0.60 molar, okay? And if your sulfuric acid fully dissociate into 100% dissociate into H plus ions and sulfate ions, well, what would be the H plus concentration if the dissociation is 100%? Well, each 1 mole of this H2SO4 would produce you 2 moles of H2 plus ion. So if the concentration of H2SO4 is 0.60 molar, the H plus then is 1.2. 1.20, 2 sig figs, 1.2 molar. And these are the simple, okay, concentration calculations converting between molarity, moles, liter of solution, and grams of compounds. This is what we do. All right. Another typical lab technique that people always need in a general chemistry lab is dilution. Okay, what is a dilution? What happens in dilution? Well, I'll give you a realistic lab scenario. Okay, you're trying to make a solution for your experiment. Okay, and you're looking for the compound, the solute, and trying to dissolve it in water. Unfortunately, let's say, okay, you're making a sodium hydroxide solution. Okay. Unfortunately, you found in your lab you don't have any solid sodium hydroxide, so you can't go by measuring a certain amount of grams of sodium hydroxide and then trying to dissolve it and trying to get your solution. Okay, let's say we just don't have solid, okay, sodium hydroxide. No. You look around, I still need to make this solution. Oh, guess what we found? Okay, I need to make a solution concentration of, let's say, 1 molar. Okay, but I looked around, I found that I don't have any solid sodium hydroxide, but I do have a 10 molar sodium hydroxide bottle. How do I go from 10 molar to the 1 molar that I wanted? Okay, and of course you use salt rate. Okay, dump water in it. But how much water should I dump? How do I figure out, okay, if I'm giving numerical conditions of different concentrations, different volume of stuff? No. And yeah. Let's also look at an example here. 50 milliliter of 12.0 molar NaOH is diluted into 250 milliliter. Okay, calculate the concentration of sodium hydroxide in the diluted solution. Okay, so how should I deal with a dilution situation? Okay, now what do we focus on? Well, what happens in a dilution situation? In a dilution situation, you add water into your aqueous solution. Okay, the more water you add, the more dilute the solution would be. Okay, during that process though, because the only thing you added was the solvent, water, okay, now you can be 100% sure that your total amount of the solute, sodium hydroxide here, okay, is never changed. And that is going to be the basis of our dilution calculation. Our dilution calculation have the equation of M1 V1 equal to M2 V2. Molarity of the original solution times the volume of the original solution should equal to the molarity of the diluted solution times the volume of the diluted solution. So let's see. This would be my V1. This is my M1. This is my V2. And this is my M2 that I'm trying to find out. Okay? So M2 should equal to M1 V1 over V2. So stick your numbers in. 12.0 molar times 50 milliliter Normally, for a regular concentration calculation, we always turn our milliliter into liter, okay? But in dilution situation, when you have volume on top and volume on the bottom, in this case, 250 milliliter, okay? And you realize that, oh, okay, my volume units are the same, and I can cancel them. Does it matter if you use milliliter or liter in this type of calculation? The answer is no, doesn't matter. Okay, so 12.0 molar times 50 milliliter divide by 250 milliliter, and you ended up getting the concentration, and that is the concentration of sodium hydroxide in the diluted solution. It's 2.4 molar. Keeping 2 sig Figs. Okay? And as long as you're dealing with dilution, this equation always works. And you can be 100% sure, okay, any dilutions thrown your way in this Chem 115 class, okay, you would always get 3 of the 4 conditions. So no 3, calculate last one. And that's how dilution is done. We'll pick up from here on Friday's lecture.